You cannot do that. So you can do something in exponential time and do better. But if p is not equal to np, then you can't do any better in polynomial time. So you can check. So basically there are only so many ways of generating clusters, and you can check every subset possible ways of decomposing the points, and they're exponentially number, and each of those you can find the optimal center. So that's exponential time. But so welcome back, everyone. So we were talking. So let me kind of start over again, and we're talking about these assignment based clustering. Okay, see this, and so the idea is that you start with some data set, and I think I called this P last time, but in the notes it might be X, and then you also have a distance D, and so often we'll assume that the distance is a metric. If it's not a metric, sometimes you can still use the algorithms, but but things might work in ways that are they're not as predictable. So the distance takes in, think of taking any 2 points that these from the domain that the data set lies in, and it tells you how far apart these are, and the goal. The goal of this is going to be a set of centers C, and so then given the set of centers C, you can define this function phi of C, which is defined for any point in your data set. It gives you the arg min center in this set of the distance from P to this center, right? So this arg min is saying, so the min is saying, here, let me draw an example here. So the point set P might look like this. Okay, and then you're going to pick, say, 3 centers. These points here are now in blue. And then these blue centers defines a map. So this point will be mapped to the closest center. So for instance, this point here will map to this center because it's closer to this one than it is to this one or this one. And in fact, there's this nice way you can draw in. You can draw what's called a Voronoi diagram, which kind of divides up the space. And you can think of drawing these separating planes in between the points, and then they kind of fully decompose the space. So there should be a straight line here. And so if a data point is on this side of these lines, then it maps to the center, and that describes this function phi here. It's kind of equivalent to the decomposition based on these lines. Okay, so if we have these centers, and that's this blue set of points here, then it defines this clustering. All of the points here are in the cluster with this center. And the minimum is the distance, and the argmin is the object here that minimizes this distance. Okay, and so I drew this here in 2 dimensions with the Euclidean distance, but this could be you can define this with any distance, right? Okay, and then I mentioned once you have this, then there are a couple of formulations of clustering. So what you want to do is define some cost function. So you want to define a cost and then find the set of centers that minimizes the cost. Okay, so find cost. So for a cost function, then you want to find the centers C that minimize the cost. And so we'll define three common cost functions. There's the k-center cost, and this is what we briefly talked about before. This is what we briefly talked about on Monday, and that is defined then the cost of, say, a point set and a set of centers is going to be equal to the maximum over all points in the set of the distance from the point to the center that that point is assigned to, right? So for every point, I map it to a center, and I look at this distance, and I want to look at the maximum distance here. And this defines the cost of this clustering, right? So this point right here, this one is probably the furthest away from any one of these centers. So the distance from this point to this center defines this cost. And so you want to say every point is close to some center. And I don't want to have any sort of outliers I haven't dealt with. That's the goal here. But there are other cost functions that you can try and minimize. There's probably the most famous one, which we'll spend most of this lecture talking about, is called the Kmeans cost. And so this is for where the size of the set of the size of the K is the number of these centers, right? So this is C1, C2, up to CK. Okay, and so in this case, the cost function PC is going to be equal to, instead of a max, it's going to be a sum over all points. And it's going to be looking at, again, this distance function, the same as before. So look at the sum of all the distances from the point to the center it's assigned, but then I'm going to take this distance and square it. So the k-means has this squared. So if you're looking up, so often, if you go into, if you're working on some data set for some company, or, if you're a data scientist, you may be looking at some research papers to try and find specific type of clustering. A lot of papers, when they talk about k-means, they'll actually write this without the squared. And that's not actually what the k-means cost function is. And we'll explain why it's called the k-means a little bit later, after I finish talking about the k-center. There's this other one called the k-median, where now the cost is defined as where it's the sum again, but this time it's not squared. So I'm just looking at the distance, and so all right. I want to highlight the k-means has the squared function here, and so this squared function has a couple of consequences. It turns out the k-means cost function is a lot easier to come up with an algorithm that optimizes this for than the k-median cost function. The k-means, though, is so that there's a reason you would write them in this order, right? Think of this order from k-center, k-means to the k-median. What would happen if I changed this squared to this 2 to like a 3? Or if I changed it to like a 10? Or maybe I changed it to like 1,000. If I change it to something like 1,000, it's going to start looking like the same thing as the k-center cost function. This k-center is really saying, I really care about these, every point is close to one of the centers. I can't have any, I don't think there are any, maybe it says I don't think there are any outliers. I should be able to capture every point with one of the centers. Whereas the k-squared said, I'm kind of averaging over all the points, and this one is averaging the square, this one is averaging just the distance. The square is saying that a far distance, when you square it, it makes its contribution much bigger than a small distance. small distance, they're all weighted by the distance. When you square it, then so if I have like 2 points, this one is a distance of 10, this one's a distance of 1. When I square distance of 1, it doesn't change. When I square distance of 10, it becomes 100. Right? So that one becomes more important. This k-center says the only one that's important is the furthest one away. This one says the further ones are somehow more important, but all of them matter. And this one, the k-median says they're all all of them are important, but I don't want to weight one more than any other one. And so there's kind of a progression going down here. This k-median one is going to be more robust to outliers, but it's a little harder to actually come up with an algorithm for it. So it's kind of good to keep this in mind. This is kind of similar to when we had like the L2 versus the L1 cost function. We'll talk about later in the lecture on compressed sensing, where again you'll see doing something that looks more like an L1 is going to work a lot better for dealing with some noise in the data. And that'll be true here as well. Okay, so let's now talk about an algorithm for the k-center costs. And I'll just write up this cost up here again. Is going to be the max of all points of the distance from P to phi P. Okay, so we're going to try and we're going to find a set of centers. So we're going to find a set C of size C equals K to make the cost small. And we're going to try and minimize it, but we're not going to come up with the true minimum. The true minimum is a very hard combinatorial problem. Instead, it was NP hard to find the actual minimum in these cases. And so we'll talk about a very simple greedy algorithm that's usually attributed to Gonzalez. Gonzal. I didn't write that up. Okay. Gonzalez, maybe. Okay. Yeah, okay. I spelled that right. From 1985. Okay. And so it's going to be a very simple greedy algorithm. I'll write it up, and then we can talk about it and go through a very simple example. So, start by choose C1. From P arbitrarily. So I can choose any point as my first center. So I'm going to set my first center to be this, and what we're going to do is we're going to and now this will be an uppercase C. C1 equals this, just this one center. And in general, we're going to have that CI is going to be centers 1, 2, up to CI. And eventually, we're going to have so that C is going to be CK, and these are uppercase C's. Okay. And so now we're going to say for I equals 2 to K, we're just going to choose one center at a time. And we're going to set, so CI is going to be equal to the arg max P and P point in our data set that maximizes the distance from P to phi, and then this would be CI minus 1 of P. Right? So this is the whole algorithm right here. Okay, so you're going through this for loop. So you first choose one center. You go through the for loop, and each time through, you're choosing one new center, and you choose it as the data point, which is the furthest away from any of the centers you found so far. Right? So So let's go through an example here. So let's say these are my data. And all right, so I've chosen data that looks like it should have 3 clusters. So let's say I pick one of these data points arbitrarily and set this to be C1. Right, so now I find, so this is my first center. Now I need to go through for 2 up to 3. So define k equals 3. So now I find the point that's furthest away. And maybe this point here is furthest away from this center. So I've set this to be C2. Okay, so now I can think of dividing up this space like this. Right, now each point either is, I look at the distance of every point to either C2 or C1, whichever is closer. And so I say, which point is furthest away from one of the 2 centers? And in that case, maybe it's this one. This is further away from C2 than any of these points is from C2 or any of these points is from C1. And this will be my center C3. And then if k is equal to 3, I stop. I'm done. And so now, and then I can define this final kind of Voronoi diagram here, and it divides up the space like this. And even though maybe I didn't pick my centers optimally, maybe they would have been better in the center of these clusters, I still divided up the points well. Right? I still have a good way of dividing up the points, even though maybe the centers could have been more in the middle of each of the sets that they represent. I still did a pretty good job. Right? So this is the simple algorithm. Right? So does this make sense? It's a very, very easy to implement. And I have in the notes there actually a little bit more detailed pseudocode of how you'd actually do it. Yeah.
So C3 was compared to C2 and C1, like when you.
Yeah. So there's kind of so what's going on is there's a lot hidden inside of this step here, right? So I've written this as one line of pseudocode, but this is actually probably like 5 or 6 lines of code. Right, in doing here, right?
Because it has to iterate through all the history of centers as well.
Yeah, so I need to check. So I need to compute this phi function for each point p, right? So I need to find for every point p, I need to find the closest center. Remember this phi. Remember I've defined phi of c of a point. This is equal to the arg min of C in the center of D of P to C, right? So this needed to find a minimum over all the centers in here, okay? And then I need to find, for each point, I had to check all centers, and then I found the point that maximized the output of this function, right? So if you want to, do this modularly, you can define a function, takes in a set of centers, and for the point, it gives you the minimum distance. And then you call this function here, and then inside of a for loop here. That's one way of doing it, right? You don't need to modularize it that much necessarily. And in fact, it's a little bit better. You can actually pre-compute a lot of this part. You don't have to check these every step because these, a lot of the points are not going to change which center they're assigned to in between the steps. So you don't have to completely recompute this all the time. Right, so if I just ran this algorithm, right, I'm going to have a loop here of size k steps, and inside of here, this is going to take k times, right, so checking against potentially up to k centers. And then I'm going to take an arg max here, and this arg max is going to take n times, right? So this would be n times k squared, right? But I can, so I can actually do this. So let's see. I think I can get this. So I should be able to make this so it's n. So let's see. So you don't. There's kind of a simpler way of doing it. You can kind of when you're thinking of implementing an algorithm like this, what you want to do is your output is going to be this map. So you want to kind of store this map. So you think of, you have some array of all the points, and you want to assign each point to a number between 1 and k. And that'll tell you which center it belongs to, and then you store the centers in a way that's separate. Right? And so you just need to update those numbers inside there, and then given that number, it takes constant time to compute this. You then look up which center to compute the distance to. And so when you get a new center, for each point, if it was assigned to a center before, so let's say that you're considering this point here, and you're looking for, after you computed center C3, you want to update this map. You want to say, is this point closer to C3 than to any other center? Well, I don't need to compute the distance to C2 anymore. I knew it was already closer to point C1 than C2. So I just need to compare the stored value versus the distance to point C3. And because that's less, I don't need to check the distance to point center C2. So you can kind of figure out how to implement this kind of a little bit more efficiently. And so I have some little bit more detailed code inside of the notes you can see. But this, for a lot of situations, this simple algorithm is going to give you a fairly decent clustering of the data. So the one strange thing it does is it tends to, it biases towards the boundaries, or it kind of tries to pick points which are kind of further away. These points are kind of on the furthest away points in the data set from the center. And it kind of ends up picking these centers which are kind of further away. And so this is one of the main downsides of that. And it also tends to choose, if I did have one additional point out here, then this, or really far away, this would have been a center, even though it was all by itself. And that really is not describing a cluster that well. So those are kind of, it biases towards choosing these points, and that's kind of the downside of this algorithm. But if your data is really nicely shaped, like the example I had here, and this works for any distance function, then this will probably work fairly well, and it's a really, really simple algorithm. Okay, so this is, but if you wanted the centers to be more representative, then you're probably going to do something else. You probably want to center these centers, right? Somehow how to get each of these centers kind of to go into the middle of the points that it's representing. I somehow want to move them in there, right? And so the Kmeans algorithm is going to do this. So, and that's kind of one of the nice things about the Lloyd's algorithm for Kmeans, which we'll talk about next. It's, in addition to doing this, it'll also kind of give you good centers. Okay. So now the Kmeans cost function, we're still going to, or let me write up, the important parts up top here again is going to be arg min of C in the set of centers, and this is the distance from P to C, and then our cost function for the K-means, and so this is going to be the K-means formulation, and now the cost is going to be equal to the sum of all points in the point set from the distance from the point to its center squared. Okay, so now this is going to be our desired cost function here. Okay, so the typical way to solve this is by an algorithm by Lloyd. And this algorithm apparently dates back to like 1957, but it wasn't published until 1982. Like he had it just as a manuscript that people passed around, and finally someone said, you should put this in a journal or something. But it's a fairly old algorithm. And so, and we'll see it has nice properties, but it's going to be a little bit less flexible in some ways than the Gonzalez algorithm. I talked about before. This is 1982 or 57. One of these two. Okay. So in this case, the Gonzalez algorithm, it slowly built up the centers. It added one center every step. This is going to start with a set of some set C of centers, which are going to be, usually these are going to be a subset of the data set, where C is equal to K. Okay. All right, and so then it's going to have this this loop, this repeat loop here. Let me actually write this. Getting tired of the red here, so okay. It's going to repeat these two steps, okay? For all of the data points, it's going to find this phi of C of this set of centers. So I started with the set of centers here as my input, as a way of initializing the algorithm, and it's going to find this center which you should assign this point to, right? So this is the closest center for each point, okay? And then it's going to be for all I in K. So there are K centers, and for each of the centers, I'm going to create a new value of the center, and this is going to be the average of all the points such that phi of C of P is equal to Ci. Okay, so let's look at this notation. This notation is a set, right? The curly brackets means a set. It's going to consider all the points in the data set, and this line means such that this condition holds. And this condition is that the center of that this point was assigned to center Ci before. Right? So in the previous step, I assigned every point to one of these centers, and I'm saying in the previous step, if this point was assigned to center Ci, then it's dealt with in this I step, and I create a new center, Ci. I'm creating a new choice of the center here. So in the Gonzalez algorithm, once I chose a center was fixed, now I'm kind of adjusting these centers as I go. Right? So if I went back here, I had these old centers, and this average essentially allows me to move these into the center of these groupings. Okay, and so and you do this until the set C is unchanged. So that if this previous step does not, if the assignment of every point to a center is the same, then it's going to give you the same averages. So if this stops, then you stop. This isn't the only condition when you can stop. You can stop, say, after 10 or 20 steps. That usually works. Or if the distance that the centers have moved is small enough, then some people will stop then, because sometimes it can kind of iterate for a while. Right. So this is the algorithm. So this is it. It's again a very simple algorithm here. Right? And so this has the advantage that it's going to kind of keep optimizing these points towards the center. When I'm going to the second step here, this averaging is moving my representative towards the kind of the center of all the points that it's representing, which is great. But when I do this, when I change the center, then this assignment may change. So that's why I need to loop. so the assignment of which point maps to which center may change when I change where these initial centers are. And so that's why I need to kind of repeat until this is unchanged. Okay, so what properties can we say about this algorithm? Is this algorithm ever going to stop?
Maybe.
Maybe. So you think it might not stop? It turns out the algorithm will always stop, and there's a cute argument why it will always stop. The thing is, we're looking at this cost function here. This cost function, which is the sum of the squared distances in the assignment. Okay? And my argument is that this cost function is going to decrease or stay the same every time I run this step or this step. It's always going to go down. Okay, so for the first step where I'm doing the reassignment, this should be clear. Every time I reassign a point to a different center, then this cost is smaller. Right? So now this map is kind of before it was kind of implicit that every point was mapped, based on the distance. Now I'm physically reassigning it here. But I'm always computing the optimal reassignment. So this step causes it to go down. And then the reason why you look at the sum of the squared distances is because given this set of points, this average is the optimal center. So by changing the center point to be the average, that minimizes this distance. So that means this can only decrease again. So every one of these two steps, so every step is going to decrease the cost. Decreases the cost. Right? So every step decreases the cost function. Okay? And so that is enough to say that this will eventually terminate. Will terminate because there are only a finite number of ways you can actually assign these. You can assign these points into different clusters. It turns out the number of ways you can do it is exponential. So it's a huge number of ways you can do it. So it might run for a really long time. And there's a bunch of people who spent their PhD thesis was partially coming up with examples where this algorithm takes an incredibly long time to run. And there's a chain of papers where people kept showing worse and worse examples. So you can actually create examples where this takes a huge number of steps to actually converge. Now these examples are all very kind of extremely silly. They're data points that you wouldn't want to cluster, and they're very adversarial. You have to get the points just right. And the calculations to show this work is kind of very detailed and nuanced and goes on for pages and pages. But there's not a great bound on how long this will take to converge. Usually it converges pretty fast. And so I'm saying in practice, when people run this, usually in 10 or 20 steps, maybe even 3 or 4 steps, it will converge. Right? If I showed you on this example back here, and we ran an example, which is a little hard to do on the board, but if you did it, this would probably converge in 3 steps. Even if I started with all 3 of the centers all grouped together, the first step would push them far apart, and then they would have about the right. It's going to have about the right clustering, and then the averaging will move into the centers, and then it will probably stop. Sometimes there are a few points on the boundary which will go back and forth a few times, but after a few rounds, it's usually pretty close to being done, if not completely done. Right? So this usually works, but there's some examples where it won't actually get you what you want. It will actually get stuck in a non-optimal clustering. Let me see if I can draw an example of some case where this could happen. Let's say there are data sets that look kind of like this. Okay, and I wanted k equals to 3. And so if I started out with 2 centers here and 1 center here, what's going to happen is I'm going to divide the space up, in this Voronoi diagram, kind of like this. Right? And so it'd be better off, the better answer would be having 2 centers on the right side and 1 center over here. This is going to give a better 3 clustering. But the algorithm will stop in this blue location. It won't keep going. So this can get stuck in these kind of local optimum. And it sometimes happens in practice. And it's easy to draw in these two-dimensional examples, and you can kind of see what's going on. But when you have these examples where you have some abstract distance you're trying to do this with, you don't really know if it's stuck in the wrong thing. It might get stuck, and you can't easily draw a picture and say, oh, it's stuck, right? So that's one down point of it. I mean, the Gonzalez algorithm could have the same problem, right? So it might end up not doing well, but it's off by most a factor 2. The k-means can be off by perhaps much more than a factor 2. I could put these closer together and these further apart, and this would still be a problem. So the k-means might give a much worse solution than the Gonzalez. But I know that this step always decreases the cost. This always decreases the cost when I do this. So how can I kind of partially solve this problem that it might not do well?
Did you run the Gonzalez first and then run the Lloyd's?
Yeah, that's right. That's right. So instead of just starting with an arbitrary set here, use as the input the Gonzalez algorithm. If you use the input here as your first step, you're kind of guaranteed that that's a pretty good start. Now, it's a different cost function, so it doesn't exactly say something, but it's a pretty good start to what's going on here. And so then if you run this afterwards, it's only going to improve it. Right? So if you go back to this example, I had a pretty good start with the Gonzalez, and then if I run it just one step, it's going to effectively center all of these centers, and I'm going to get a much, much nicer answer. Right. So I can run this Gonzalez algorithm here. This sometimes works well, but it can sometimes get into problems because if I had this outlier point, the Gonzalez algorithm may have chosen this one as a center. And so that would have been the best for this k-center cost function, but it was not what I wanted for the k-means cost function. This center should not have been chosen for the k-means, perhaps. I didn't want to choose the outlier as one of the centers. And so the Gonzalez still didn't give me what I wanted entirely. But this works fairly well. So generally, instead of just picking an arbitrary set of centers, or often people say they'll pick a random set of centers, or they will randomly split up the points into subsets and then choose the centers of those as the starting point. It's better to start with something like the Gonzalez algorithm. And this will give you a good seeding to this algorithm. Let's see, what else did I want to say? Oh yeah, so there's another. So after this, I'm going to talk about another way other than the Gonzalez that works a little bit better as a seeding. But before I mention, there's another kind of disadvantage of the Lloyd's algorithm than the Gonzalez algorithm. What else? There's kind of another kind of assumption about what I can just do and say about the data that I didn't need in the Gonzalez algorithm. There's something else I assumed here that I didn't need before. Yeah?
That you can take an average?
Yeah, right. So I'm assuming I can take this average operation, right? This makes sense when I'm in Euclidean space. So this basically essentially assumes that my distance is going to be the Euclidean distance, and that it makes sense it makes sense to take this average. So there are other kind of distance, there are other metric spaces where you can do this, and this still makes sense, and you can still guarantee that this step will decrease the cost function. And as long as it's decreasing the cost function, then you can still have a lot of nice properties about this. But this basically assumes that you're using this Euclidean cost function. It doesn't need to be in 2 dimensions. It can be these high dimensional settings that we talked about, such as, you know, if you're doing this with this, if you're doing it with like these SIF features, which are 128 dimensional, you can still do this. It still works fine. But if I'm doing this instead with sets, right? So let's say I was trying to do this where my distance was the Jacquard distance. And I wanted to say, well, here are a bunch of things that are assigned to the same center. Let's take the average of these sets. Now, I don't know how to take an average of sets anymore, right? So this can create a problem, and this is this is not as flexible in some way. But let's say I did want to do something like this for sets. I can still define this K-means cost function. Or I can still say I don't want to do the case-center. The case-center biases towards outliers too much. So I want to do something like the K-means. How can I retrofit this algorithm to work with things like sets? So what parts of the algorithm still work, right? Well, what parts of this work? I can still do this first step, right? I can still assign, if I know the centers, I can still assign every point to the closest one, because this is just defined by a distance. I just take an argmin. For every center, I can check the distance, and I can, assign to the closest one. So this step works fine, right? The step I need to change is this average step. I need to somehow find all the points assigned to one of the centers and create a new center, which hopefully improves on this.
If you do not care the cost, you can just define it using the tool, find the point closest.
Yeah, so I can still, you said if I don't care about the cost, but I still do care about the cost, right? So I can say, I can check, instead of this as an average, I can say, so in step 2, I can set CI equals arg min of, let's just say generically, let's say these are the points that are assigned to center CI in the previous step. So of these points, I'll take the arg min of this, so of again, the sum over these points of, let's call this a P prime. So of the distance from P prime to P, right? So I can find the point which minimizes this squared, that minimizes this sum of distances. And this is a little bit slower. But I can do this, and that will always guarantee to either decrease the cost or keep it the same. And so this will work pretty well, actually. You can get centers, then they're going to be elements of your data set. But maybe this is good. You want a set of centers that you can interpret somehow. So then they're elements of your data set. And this actually works pretty well. It still has the same kind of convergence guarantees. And again, this step, doing it this way is going to be slow. So what often people will do is maybe they won't check this out of all points. They'll maybe check a subset of the points, or they can kind of, maybe on the first time through, they kind of figured out which points had a small distance, and then use those points to check. And then kind of just refine based on that. Because usually after the first few rounds, it's only going to be changing a small amount, the different assignments. So maybe only if there's a large change in how the clustering structure do you kind of do the full check. Otherwise, you only check a few points if it minimizes. And that'll be faster. And it may not give you the optimal answer, but it usually will work pretty well. Again, if, you kind of want to always remember something I said in the first lecture that on clustering, that if there is a good clustering, most algorithms work pretty well. If there's not a good clustering, almost no algorithms are, no algorithm can find a clustering that's not there, right? So you kind of just want something that if there's a good clustering, you're probably going to find it. And so it's okay to kind of play with this a little bit. The only difference of using these things of either finding the absolute minimum or not, or running the generic algorithm until it completely stops, is going to be a very small difference usually in how good the clustering is. So it's often okay to kind of terminate this before it completely converges, or to kind of do some, not check every possible point to be a center if you're in this setting which is discrete. Okay, so let's, the kind of the last version of this is I'm going to talk about, instead of using the Gonzalez algorithm to center this, I'm going to talk about another algorithm called Kmeans to use as the initialization instead. So this Kmeans algorithm will give you an initialization which in general and in kind of in practice works a little better. It's going to be similar to Gonzalez, but instead of minimizing, kind of working towards the k-center, it'll work towards the k-means objective. And it'll still be very fast. And it'll give you a good initialization, and then when you run this, you'll kind of be able to say some nice things about it. All right. Okay, so k means plus. Sorry, my. Okay, so k means plus. And so this was by Arthur and Vasilevsky. I think this was around maybe 2006, I think. So this is a fairly recent thing. So it's going to be nearly as simple as doing the Gonzalez algorithm. So we're going to choose C1 from our set P, and so this step can again be arbitrary. Arbitrary. So I'm going to choose the first center, C1. C1 is going to be arbitrary. Okay, and then the question is, I'm going to build up the centers one by one in the same way before. And so now I'm going to have for I equals 2 to k, then I'm going to choose C1 from P proportional to -1 squared. Okay, and so this is at random. Okay, so this is now a randomized algorithm. Okay, so let me break this down a little bit again here. Right, so it's again going to be fairly simple. I'm going to pick the first one arbitrarily, and then I'm going to choose each new center one at a time. But instead of always choosing the furthest point, I'm going to choose it randomly but proportional to a distance. So the further the distance is from the center, the more likely I am to choose it. Okay, and so, if I want to take the max, you kind of knew how to do this. How do I do this randomly choosing these according to this proportional at random? So let me break down what doing this actually means a little bit, okay? So the idea is that you think of having points P1, P2, P3, up to Pn, and each of these points has some weight, W2, W3, up to Wn. Okay, and this weight, so weight of Wi is going to be exactly d of p, ci minus 1 in this case, times p squared. Okay? And so I'm going to then choose pi with probability wi divided by uppercase w, where uppercase w is going to be the sum over I of all these lowercase w's. Right? So all these weights will add up to some big W, and I choose it with probability, its weight over the sum of all the weights. Okay. So all I've told you now is just what this means to be proportional. I haven't told you how to do it yet. Right? Given a set of points with all these weights, I need to choose a point proportional with this probability. Okay, so before I tell you how to do that, if one of the points is a center, right? So let's say that C1 said P3 is, so this guy is equal to C1. Then what is weight W3 going to be? So if this is a center, then the weight is 0, which means I'm never going to choose it, right? And if it's really far away, the weight is going to be high, right? So so the weight is going to be high if the distance is far. If it's very close to the center, the weight will be small. Small probability I choose it. Okay, so how do I choose a point according to these weights? What's kind of a way of doing this? How do I do this? And remember, all I'm going to need to do is I'm going to have one kind of built-in operation. I can choose some value u uniformly between 0 and 1. So I can create think of creating a random number between 0 and 1. In practice, in theory, you can only generate random bits, but you generate enough bits, and those describe the binary decimals. But anyways, you can think of getting some random real value between 0 and 1. And given this, it's going to be enough to generate these, to select one of these points proportional to this weight. Yep?
You can sort the weight, the fraction wi by w descending order, and then you can iterate until the value is basically, for each value you check whether it's less than that fraction. If it is, then you choose that point. Otherwise, you increment the value by the fraction and go. I'll restate what you said, but you actually don't need to sort the points first. So there's no sorting necessary. So the right way to think about it is that you think of there's this line or this region between, this is hard to draw with this stylus here. All right, so there's this region, and it goes between 0 and 1. And what I'm going to do is I'm going to fill in this with the weight. So let's call this number, let's call it Ri. So Ri is now a value between 0 and 1, and R1 goes from 0 up to this point. And then I go, and then I draw another region here. This will be R2. So this point here is R1 plus R2. This is R1. And then maybe R3 is here, and then I go up to, this is Ri, and this is the sum for j equals 1 up to I of Ri. What? So I can think, I'm not talking about how to do it yet. I'm kind of conceptually laying out how this is going to work, right? And then this is going to go up to Rn. And each of these is going to occupy a block between 0 and 1 based on the probability I choose it, right? And so if this point was a center, then I basically skip it. It has 0 component here. So now when I choose this random unit vector, it's going to be a value between 0 and 1, and it's going to correspond with some spot between 0 and 1. And if it falls in this range that's claimed by R3, then I choose point P3. Right? So if this will be my value U, it's going to fall in here someplace. So now, once I've chosen a value U, it defines one of these points that I pick, and this will choose it with the right probability. The probability it fell in the region associated with P1 is exactly this value Ri. This P1 was exactly the value R1. The probability it fell in here was exactly this weight W1 over capital W, right? So this allows me to choose these right way proportionally. Okay, so now how do I actually do this computationally? One way of doing it is to kind of lay these all. Is to kind of check if U is less than R1. So for I equals 1 to n, if U is less than Ri, then select Pi. Else, then you get U minus Ri. So I'm kind of essentially subtracting off the effect here, and that's sliding everything. It's kind of sliding everything over. So I'm moving U over. So if that didn't happen, then I moved U over this way, but I've also moved over all of these boundaries, a distance Ri. And so then it kind of resets. So there also the other option is to say check if it's less than Ri plus all the things before it, and then you don't have to change U, but you need to kind of keep a counter. So you can do this, and this takes linear time. You should see also you can if these are fixed, you can pre-process them and then search for this. You can search for it using a binary tree, and then this only takes log n time. But for this algorithm, they're going to be all updating every step. Or they are mostly going to be updating. And in that case, it's not worth it to try and pre-compute like this structure in this case. But in other settings, that'll be useful to pre-compute and build a binary tree so you can do this more quickly. Yeah.
You might have already answered this, or this might be a little off topic, but wouldn't we be worried about like high dimensional space with all the points? So if you have to have a cumulative distribution function, basically that's what it is.
Yeah.
And it's ranging, so each of the probabilities gets smaller and smaller and smaller. You can only compute so much that way that it might just result to 0. Does that make sense?
Yeah. So this only depends on the distance, right? So this, there are some weird things that happen in really high dimensional space, kind of most distances tend to look very similar to each other. And more what you're saying is if you have a lot of points, then all of them are going to have a really small window. So each point's going to have a very small chance of being chosen. Right, but you think, I'm going to choose a small number of centers to represent these. It doesn't matter if there are a bunch of similar points, it doesn't matter which one I choose. So you should think of the sum of these points instead of the individual ones. And so that's really what's going on here. I'm really optimizing this sum of squared distances, right? So if there are a lot of points in the same region, then these are going to essentially they're only going to contribute to the cost function if there are a lot of them, and then there are many chances I'll hit them. I don't care which one I choose as long as I choose one of them, right? So let's go through an example, kind of just to think about how this will work. So start with my my data points are kind of like this. And I have a lot of data points in each of these clusters, and there should be 3 clusters, but there's also this one outlier out here. Okay, so now let's say I chose the first data point here, okay, arbitrarily, this one. And if I chose it at random, it's very unlikely it's going to be the outlier. So maybe I do the first one I choose at random. And so just by the fact that there's only one outlier out here, or there's a small number, there's a small chance I'll pick it. Okay, and so now once I've chosen this one, let's kind of look at this, this way of decomposing this probability from 0 to 1. Now there are a lot of points, so I don't want to think of drawing all the cells, but what I can think of doing instead is saying that there are some points here, and let's say there should be these different clusters. This was cluster 1, or I shouldn't use, that means center. So let's say that this was in set 1, set 2, and set 3, and then this was set 4, which is an outlier. And what I'd like is to kind of pick 3 centers, one each of these sets, and then just deal with this outlier. Maybe it'll help me identify it later. Right? So this first region here, after I've chosen this one point, this may be the total probability of set 1. And then I have going to have 3 other regions, right? So it could be that this region here is the total probability of choosing a point in set 2. This region here is the total probability of choosing a point in set 3. And then this one is set 4. It's further away, so it has, this is a single region for this point, so it gets more weight because this single thing is longer, but there's only one of them. Now there are more of these points in set 3 here, and even though each of the bins is going to be, say, smaller than the one bin in set 4, there are many of them, so they add up to kind of do. And the proportional they add up is exactly because it's based on the squared distance. It's the same as the cost function I'm trying to optimize. Okay, and this was set 3, so if I choose my random point, it's usually going to wind up in set 2 or set 3. Sometimes it'll wind up in set 4. That's unlikely. Sometimes set 1. You know, if it's in set 1, I'll probably end up shifting one of the centers to one of these other sets. If it's out here, I might not. Right? So there's some chance I'm going to end up out here. Now, what's going to happen if this outlier point goes really far away? Yeah, if it goes really far away, then this probability increases. But at the same point, because of the cost function I'm trying to optimize, then that's so far away, it shouldn't fit in any other cluster. I should have its own center. And so, you know, so I should be picking that point with higher probability to give me a good understanding of the Kmeans objective that I'm after. So this is kind of choosing points the right probability. And so if you go back to this Kmeans plus, yep.
How about we divide each distance by the cardinality of the set itself? You know, value of 10 balls, we divide everything by 10 balls and normalize in some sense.
So you want to divide every distance by, I didn't totally understand the question.
So if there's a point in set S2,
yeah,
there's a distance with the Sn, right? We divide that distance by the number of elements in set 2.
Right, the thing is I don't know the sets ahead of time. So I want to discover these sets. And so this is kind of automatically doing this without really knowing that the sets are there. Yeah, so if I knew the sets, then I could actually formally create these buckets and then choose it with just the right probability. But you know, it's kind of doing that for me automatically without knowing the sets, which is great. And if I knew them, then I wouldn't need to do this, right? So yeah, but that's kind of the right way of thinking about it, though. These are all approximately going to have the same distance, anyways, just based on the cost function, on how the weight is done. Right. Okay, so let me just mention a couple more things about this. So if you do this Kmeans as your initialization step to the Lloyd's algorithm, or if you just run this by itself, I think, then it's known that then you're going to get something like a O of log n approximation, which is to the best k-means center. And so it depends on n, but logarithmically, this is really not a great bound. But it says that just doing this with it's a randomized algorithm, so there's some probabilistic guarantees. This is already going to give you, with some probability, going to give you a good clustering. And probably what you want to do is try running this and doing this is without running Lloyd's algorithm. And if you run Lloyd's algorithm afterwards, if you do plus Lloyd's algorithm, which is this iterative algorithm, then it gets to an 8 approximation. And this is with some probability. So what you want to do is you want to run this algorithm to choose the initial centers and then run Lloyd's algorithm and do this a few times. Maybe do this 5 or 10 times and take the one that has the smallest cost function and at the end, and that'll give you kind of guaranteed to give you an 8 approximation. So, and you know, 8 is a really worst case bound that handles even these crazy adversarial examples that people spent, several years, creating. Even if you get these crazy examples, you're still going to work. You're still going to get a guarantee. If it's one of these data sets that you actually want to cluster, it's going to give you an even better. It's going to. In those cases, you can show it'll give you an approximately optimal answer, like within any epsilon guarantee. Instead of 8, it'll be an arbitrarily small number. So if it's well separable, there's some technical definitions for this, then it's always going to give you a good answer. Okay, so there are a couple of more things I want to say just to wrap up. So just to wrap up the lecture. So first of all, this example I have here, this is kind of an example where you can see what's going on. You have these 3 main clusters plus an outlier. And your goal was really to optimize the k-means cost function. You decided that's really what I want to do. It actually models something where I'm building these distribution centers in the middle. Like if you're Walmart, you put the distribution center in location, and then the cost is the delivery cost away from the distribution. So it really means that is what you want to optimize, and sometimes that's the case. Should I be putting k, is 3 the right number of centers for this? If that's the case, I probably want to have 4 centers. I want to have these 4 groups. I have these 4 distinct sets. And in that case, you're probably going to run this until, if I run this and I chose 3 centers here that are inside of these 3 groups, then this new, and I drew this probability thing again, what's going to happen is that set 1 is going to look like this. Set 2 is going to look like this. And set 3, this is set 3. And then all the rest of this probability is going to be pretty high. This is all going to be if I chose a 4th center as choosing S4. Okay, it's going to be really high out here. And so I'm almost very likely going to choose that as my next center. And you can one way we thought, what is the right value of k? We can look at this cost function and see when it's really dipping when it changes very drastically when I change the value k. And by kind of looking at these, you'll kind of see at some point all of these distances, all these bins become really small or about the same size. Or if there's some that are much bigger, then that means that's a whole set of points which are not well clustered. And if I can change it by choosing 1 point, then I should do it. If I can't, I probably already have enough clusters. Or you kind of look at that or maybe see what is that cost function and that trade-off between, say, building a new facility versus reducing the average drive time for delivery within that region. So you can kind of look at these cost functions to tell you what is value k. Don't just run it blindly with the value k. Okay. The other thing is that the other one I didn't really talk about was this k-median cost function. And I said this is going to be more robust than the k-means. right? I'm not squaring the outlier, right? We'll do an example on the homework. I think the next homework, which I'll try and get out next week, I think. It's if you put an outlier even this far away, because I'm squaring the distance, I'm almost always going to choose this outlier. This is actually going to have, the picture is not going to look like this. This region it's going to look like this even when I only have one center, because the squared distance is just going to be so much more. The K median is going to be much more robust, and but the problem is if I look at this Lloyd's algorithm, this average step is no longer the right way to optimize this. I want to do something else. I want to minimize, the average has this property, it minimizes the sum of the squared distances. And people often think it minimizes the sum of the distances, and there have been lots of kind of weird historical mistakes based on that. But I need to compute something more complicated here. Now there's a way to create something called an L1 median in high dimensions, but it's actually, you can't compute it exactly. There's no closed form solution for it. You have to kind of run another iterative procedure in order to find that. And you could replace this step with that, and that's kind of a nice algorithm to do the K median, but it's less pretty and less nice, and that's generally why people don't use it. But it's probably a cost function that makes more sense. So it's kind of, if you don't mind the extra iterative step, replacing the average with something that iterates towards that, and there's a cute way to actually optimize that, then the K median clustering will probably give you something that's more robust to outlier points. So on next week, Monday, there's no class. It's a holiday. So I think it's President's Day. And Wednesday, we'll talk about spectral clustering, which will be a very different class of clusterings after that. Thanks.